We demonstrate GEDet, a system that can detect multiple types of erroneous nodes with only a few examples. There are several challenges of graph node error detection. First, erroneous nodes are characterized by more than one type of errors, such as violation of data constraints, misspelling. Such a diversity cannot be fully captured by a single model. Secondly, it is often difficult to obtain a full set of correctly labeled examples over real large graphs. We treat erroneous node detection as a node classification problem. We denote VT as training nodes with labels of correct or error. In particular, for error nodes, we know their correct counterparts. Our problem becomes a semi-supervised task to determine the labels of test nodes. GEDet then enables graph data augmentation. It has an error generative model H that generates synthetic erroneous examples. The learned transformations capture various types of errors from training data. GEDet also consists of a link inference model L that infers meaningful connections as long-range dependencies to complete the graph, which mitigates the impact of missing edges and facilitates graph representation learning. We use graph augmentation to enrich training examples and node neighbors, which enables GEDet learning representative embeddings from only a few examples. After graph augmentation, we leverage graph autoencoders to generate graph embeddings and feed these embeddings to a generative adversarial network. In the adversarial error detection, by forcing the discriminator to differentiate not only error and correct, but also synthetic and real labels, the GAN model further improves the decision boundary for error detection. Now we demonstrate the GEDet through a web GUI. There are two modes we would like to walk through. The first mode is automatic mode. In the automatic mode, there is no need for manual effort. We show an example of error detection in DBpedia with entity types as species. In the model configuration, GEDet supports loading a pre-trained model or train one model from scratch. Users only need to provide a few examples with label information as input. These examples can be collected when users inspect nodes in the graph view or suggested by invoking individual methods such as constraint violation or anomaly detection. User can also optionally provide transformations that represent how errors are generated. If users haven't provided any transformation, GEDet can learn such transformations in the graph augmentation step. Here we just load a pre-trained model. The automatic mode returns the top 5 erroneous nodes with error attributes highlighted. GEDet allows users to select a specific error node and visualize an induced subgraph, where nodes are this selected node and its 3 hop neighbors. Users can inspect the information of the erroneous node, such as attributes, values, and its neighbors. GEDet can suggest values that are likely to be correct based on data constraint match or string key value pair match. We click the corresponding transformation, we can understand why this attribute is detected as an error. The right-hand side attribute value suggests the most likely correct value should be animal according to data constraints. Now we move on to the interactive mode. In this mode, GEDet asks users to provide labels for some hard examples. If users cannot provide labels purely relying on domain knowledge, they can inspect similar nodes for this hard example, which is returned in the graph augmentation step. The labels of similar nodes suggest feedback. After the interactive training is finished, in the result analysis, we can observe how F1 score increases as epochs go up. In the embedding view, we break down the error labels into different erroneous scenarios. For example, blue indicates the data constraint violation, whereas red indicates the string noise. Each individual method only can cover a single color. We can clearly see that GEDet can successfully detect the erroneous node under multiple erroneous scenarios. In this example, GEDet can detect 15% more erroneous nodes that cannot be detected by traditional methods. As confirmed by the high recall, the performance of GEDet is significantly better than the baselines, such as graph constraint violation or outlier detection, where the F1 score is improved by 25%. GEDet is based on the big data paper GEDet adversarially learned few-shot detection of erroneous nodes in graphs. We look forward to inviting users to experience the high usability, unique features, and excellent performance of GEDet as the first few-shot detection system for the challenging error detection problem.